All right, so in this function, we talk about linear functions and its applications. Right. So I hope that after this lecture, I could be able to identify linear functions. Okay. And from the linear function, we're going to calculate something called the average rate of change to identify linear functions. And we're going to build linear models using verbal descriptions. So I briefly mentioned about this one in the other class last week, I think. So I want to mention this again, that I want you to be able to identify or see the difference between expressions, equations, and functions, right? Because they serve different meaning of different problems. Okay, so for linear expressions, that this is the expressions that I'm going to use. So mx plus b, right, without equal to anything, just by itself, mx plus b, this is called the linear expressions. Why is linear? Because the variable x in this case is raised to the first power. Okay, that's why this is linear. But we need to impose one condition here, that is m is different from 0. If m is equal to 0, there's no longer a linear expression. Right. If m is equal to 0, you only have b, then that is just a constant. Now you take mx plus b and you set that equal to 0, and you have a linear equation. Then again, in this case, you have to impose the conditions that m is different from 0. Now you take mx plus b and you set that to an output, you have a linear functions. So alpha back is the output, is equal to mx plus b. Again, this is m different from 0. Now, in general, functions that are not linear are called nonlinear functions. Right, you have x squared, that's nonlinear functions in general. X cubed, nonlinear exponential functions, nonlinear functions. Logarithmic function, that is nonlinear functions. Right? So, all right. So linear function, you have seen this many times, even in this course, when we do in lecture 6, we do equation of a line. So there are 3 forms when you find the equation of a line. That is point slope form, slope intercept form, general form. You have horizontal line, vertical line. I'm not going to go over this again. It's this table. It's just a summary of what we covered in lecture 6. Now, the next concept I want to mention here is the average rate of change. So linear functions have constant rate of change. Have constant average rate of change. And average rate of change is defined to be. So again, you have seen this formula already when we talk about how to find slope of the line between 2 points. That is change in y over change in x. Or the notation for change in y is delta y. And the change in x, the notation of that is delta x. So this is y2 minus y1 over x2 minus x1. So this formula to calculate average rate of change is the same as finding the slope of the line going through 2 points. Right, so this is similar or equal to slope of a line going through 2 points. So the formula should be the same. I've seen this formula before. Now, how many of you drive to school every day? Right, so can I ask you questions? Like how long it take you to go from home to school? 30 minutes. How fast do you drive using? Give me a number. 70. Right. So when your friend says 70, right, is the number that he get me is called the average velocity because he doesn't know the exact value at any given moment. Like let's say he leaves the house at 7 o'clock in the morning, doesn't know the velocity at 7:01 or 7:02 or 7:03, but overall he knows that the average velocity, how fast you need to drive, is 70 miles. That is the average change in this case. In calculus 1, you will learn another concept called instantaneous velocity. Now, when you drive with your friend and you see your friend driving fast, like, dude, how fast did you drive? He said, oh, you look at the dashboard and say, oh, 70 miles. That instant, that moment is called instantaneous. So that's two different concepts. So in this case, we talk about average velocity or average rate of change for that matter. All right, so you can apply the formula for average rate of change includes the value presented in this table. All right. So here you want to compute the average rate of change of functions, or in this case, the average rate of change of the populations with respect to time. So you have a table of value here. In the first column is time, the second column is populations. So this is the bacteria populations, obviously. All right, so how could you find the average rate of change? y2 minus y1 over x2 minus x1, given y2 in this case is 0.12, y1 is 0.09, x2 is 1, x1 0. Now that's for the first two values. The next two values, this is something y2 minus y1 over x2 minus x1. And then again, the next two values, y2 minus y1 over x2 minus so on and so forth, to see if there is a constant slope or constant rate of change. Because if there is a constant rate of change, then you can define that the functions that you can use to fit this data. You okay with that idea? Understand why we do what we're doing? All right, so for the first set two data, you have 0.12 minus 0.09 over 1 minus 0. This is equal to 0.03. For the next two values, you do 1.16 minus 0.12 divided by 2 minus 1. This gives you 0.04. So just by these two values, you see that the average rate of change. But let's continue calculating a few more values to see what happened. All right, so 0.22 minus 0.16 over 3 minus 2, this gives you 0.06. And then that's it, right? Three values already indicate that that's not going to be a linear functions. So from here, from this calculation, you conclude that since the average rate of change is not constant, the function is not linear. Right. Why do we learn all of this kind of calculations on the functions? Because remember, in reality, we don't have the luxury to have like all the nice curve. What we have usually, most of the time, what we have is data. Okay. Now, with a bunch of data, we need to use different technique so that we can help us from the data, help us make the decision in the future. Okay, so for this data, this calculation, we say that, okay, we're not going to be able to use linear function to fit this function into the data. Therefore, we need to move on to the function for different calculations to find the best curve to fit into the data. All right, so let's do the next example. So we want to calculate the average rate of change of this function. So this data or this table have the age, so 20, 30, 40, 50, 60, 70, right? And the maximum number of bits for each age category. Now do the average rate of change again, the first two data and then the next two, so on and so forth. All right. So compute the average rate of change of the functions. So the first one is 47.5 minus 50 divided by 30 minus 20, have negative 0.25. Now the next two values, 45 minus 47.5 divided by 40 minus 30, you will get negative 0.25. So it looks like it's constant, okay? Because it looks like it's constant. You look like they have the same number. You need to complete all the calculations to make sure that it's actually the case. All right, so for the next two values, you have 42.5 minus 45 divided by 50 minus 40. That's negative 0.25. You have 40 minus 42.5 divided by 40 minus 30. Sorry, 60 minus 50, negative 0.25, and 37.5 minus 40 divided by 70 minus 60. This gives you negative 0.25 as well. All right, so they're all the same. So you can conclude that this table of data fit a linear functions. So the table of data fits a linear functions.